199th question of Leetcode, which is binary tree side view. Let's read the question first. Given the root of a binary tree, imagine yourself standing on the right side of it and return the values of the nodes you can see ordered from top to bottom. So if we have given a binary tree here, where the node left to it are 2 and 5, and right of this node is 3 and 4, and we have to return the binary tree, return the node elements such that we have values of the nodes that we can see from the right side over there. Let's go to the drawing explanation now. You might say, well, this is pretty easy, so I'll just go get the right node of every node, right? So go to the root node, I'll get the right node, and then continue go to the right node, and that will return me 1, 3 and 4. No, wrong. This won't work, because let's answer the question first. What does it say? It says that we are standing on the right side of it, and we have to return the values of the nodes. You can return the value you can see ordered from top down. So basically, we are standing. Let's say consider we are standing here. There's a physically a binary tree here, and we are standing here, and we have two eyes. Let's say, so we have to see. We can see from here what is the rightmost nodes that I can see from here. Well, it's 1, 3 and 4. If there was a binary tree, let's say if there was a binary tree kind of like this, let's say this is a value and this is a value. Of course, there's no, let's say the value for this is 4, and value for this is 5, right? You might say, oh, there's no right node of this node, but from here you can see that this is the node we can see from this level, and this is the node we can see in this level, the rightmost node of every level, right? So we have to return 4 and 5. So we can't just traverse the right of all we can't just traverse right of every node you see, right? We have to see the last node in every level. So now we understand the question. So what do we have to do? We need an algorithm or code of some sort where we need to get the last node of every level. So the last node of this level 2 is 3. The last node of this level is the root binary itself, and the last node of this level is 4. The last last node in this level, right? So now we have got the gist of it. What kind of traversal can we use in the binary tree such that we can get the level of binary tree? See, there's something known as level order traversal, right? Level order traversal, where we traverse the tree level by level, right? Level by level by level. So what do we do? So it's pretty simple. So we first take the root, and we see there's only one node in this level. What are the left and right value of this level? What are the left and right nodes of this this node? Well, that is 2 and 3, right? So this is the first level. So we have got the left and right of the next level. So we start again from this traversal. We traverse 2, we traverse 3, and when we pick up 2, we have to get the left. There is no left. Oh, there's a right. So I'll just say the right node that is to be picked as 5, and we go to the next node, and we say ki by it may say we can say ki there is no left node, there is a right node. So so we finish traversing this level, and there's lastly in this level we'll start traversing from the 5 and see, is there any left? Nope. Is there any right? Nope. Is there any left of this? Nope. Is there any right of this? Nope. So what we could do is now we have figured out how to what type of level order, what type of traversal we have to use in binary tree. Now we have to consider, and we also know that we have to get the last node in that level, because that is what you will see when you stand from the right side of the tree. So we can just use a we can just use a level order traversal. I'll just go to the code, but I hope you understand the intuition behind the using the level order traversal. So what you could do is key after in traversing each level, we'll see if this node, if whatever the node is the last node in that level, we will just take a result array. So we'll take a result array and append it to this. So append it to say, for example, in this node, the last node is 1. In this level, the last node is 3. And in this level, the last node is 4. Okay. Let's do a dry run of this code first. Okay. What I'll do is keep so this is a breadth first approach. This algorithm is called breadth first approach. So what do we use in breadth first approach? Well, we use a queue, right? So what I'll do is first take a queue and insert root into that, right? And and so this is the first level. So we'll start traversing from this level and we pop it off, right? We pop it off. And what are the left and right of this node? Well, the left and right of this node is 2 and 3, all right? Levels 2 and 3, so we get the level 2 and level 3. I'll check before moving on to traversing the next level. I'll check if this node is the last node in this traversal. How do we check if this is the last node in this level? Well, we have the size of this level, which is 1, right? Since we had only one element to traverse in the first level, we'll say this is the last element in the level. And let's take a result approach. I'll take a result and append to 1. Okay. Now I go to the next level and I say that the size of this level is 2, right? And I'll take the first node out of here. I'll pop it out of the queue and I'll say, is there any left? Nope. Is there any right? Yep. So I'll append it to the queue, right? I'll append it out to the queue. I'll append it to the queue and just span this out. I'll append it to the queue and I'll check, is this the last node of this level? No, since the level size is 2 and this is not the last node, because 2 is this the last node? Nope, this is not the last node. So I'll continue traversing, right? I'll continue traversing. I'll pop this element, which is 3, and I'll consider the left. Is there any left of it? Nope, there is no left node here. Are there any right nodes here? Yep, I'll just append it to the queue. Oh, we have traversed up to this level, which is we have traversed the 2 levels. So this is the last element in the node. So what we'll do is append it to the queue, right? Append it to the result, because this is the rightmost node at this level. And we have traversed this entire level. So we move on to the next level. So till the queue is not empty and we go on to the next level. What is the size of this level? Well, the size of the level is again 2. If there was any other element, let's say there was a 3 here of some sort, the level size would be 3. So each time we would traverse only that level. So we'll take this element 5 and pop it out of the queue. Since the breadth first approach, we have to first traverse the left of this node, and we have to traverse the left and its nodes first, then the right and the right node, then their nodes first, right? So take the 5 and I'll see, is there any left? Nope, there is no left. Is there any right? Nope, there is no right. So I'll check if this is the last node in this level. Is this the last node in this level? Nope. We can see this is the last level, but it's not the last node, since we have the size, the level size, the size of this level is 2, right? So I'll go to the next I'll go to the next node and I'll pop it out. All right. Is there any left? Nope, there is no left. Is there any right? Nope, there is no right. So we don't have to append any of to the queue. I'll check if this is the last node by checking, have we traversed 2 elements, or have we traversed two elements in this level? Yep, this is the last element. So I'll just add it to the result, which is 8, which is 8. Oh, sorry, which is 4. And yeah, and I'll go to the next iteration. By the time I go to the next iteration, the queue size is empty now. So that means we have traversed all the nodes in the binary tree. Yeah, yeah, that was it. Let's go to the code and write the code, right? So I'll just create a new this. So 199 binary tree side view, right side view, right side view dot py. So I'll say if def, I'll just initialize binary tree, binary right side view, and initialize a main function. I'll take a root, right? Take a root, and I'll write an iterative function, which is I'll take a queue, since we need queue for the traversing of this element, and we say the queue contains root initially, and it will be the first level. And all I'll do is, after considering the queue, I'll take the result approach, right? I'll take the result, and I'll say while there are elements in the queue, uh, get its size level, the current level size, which can be updated by size is equal to length of queue. And I'll say for dash in traverse up to size, traverse this entire level. I'll pop this node is equal to queue dot pop the first element, since it's a queue. And if node dot left exists, then queue dot append node dot left. And if node dot right exists, then queue dot append node dot right. And I'll check if this is the last node. So I'll take the index. I'll say if I is equal to size minus 1, if this is the last node, uh, node in this level, I'll append it to the result, since this will be the since this node will be the one you see it from the right side view of this. Yeah, and append it to the node dot val. Yeah, and I'll just return result. Yeah, that is it. If I just copy this code and paste it here, I should have an answer. So let's go through code once. So we have a queue which has root, and I'll say while queue, and get the size of the current level. Each time the queue will contain that level. The code will traverse level by level. So I'll take the first level size, and I'll say if I'll pop the will traverse the entire level. Initial is 1. I'll pop the node out of it. I'll say if there is any left, append to the result, and if there is any right, append it to the queue, and get the last element. Check if this is the last node in the traversal. So so the first traversal, the I will be 0 and size will be 1. And since size minus 1 is equal to 1 minus 1 is 0, which is equal to I, we can say this is the last value, and we move forward to the next traversal. If I just run this, I should have my solution. An untap object as node dot left. Oh, there's one important check that this is why you always read the constraints, because the number of nodes in this tree range is 0 to 100. So if the root node itself is null, so we will insert a none here, and this could lead to an error. This will lead to an error, because when we pop the first node, it will always be a none. If the root is none, obviously the node will also be none, and we cannot accept a dot left property of a none value. So this threw me an error. So I had to just add a simple tag. If the root is none, I don't have to if the root is none, I just return an empty array, since I won't have any node values that I can see from the right side of this. So if I just submit it, I should have a solution. Yeah, boom, there we did it with 7 milliseconds. That is beats 98.5%. I don't understand the Leetcode metric. How does it work runtime? Because sometimes it gives you 24 milliseconds and sometimes it gives you 7 milliseconds. Yeah, so that is for today. Please subscribe. I don't know, like, share, go crazy. Thanks.